objects such as the sun are emitting, or any, it doesn't have to be the sun, it could be any hot object, is going to be emitting light at a lot of different wavelengths. So it's not a single wavelength. So we get something called a black body curve. And a black body curve, if we plot frequency on the bottom, which I'm going to use the letter nu for frequency, and then we plot intensity on the y-axis. So our x-axis is frequency, and intensity is on the y-axis. We'd see something that looks somewhat like this and then falls off pretty rapidly. And that's typical of what we call a black body curve. And actually, if we're looking at sunlight, we'll find that this is an idealized curve. We'll find that if we're looking at sunlight, it's not going to look quite like that. It's going to look more like, see if I can draw it over here. It's going to look sort of like this. There might be a dip down and then up and then another dip like that. So this is because the sunlight is moving through the Earth's atmosphere, and there's some absorption that's occurring. So the actual black body curve that we look at might look more like that. But anyway, what we can do is, whether it's the sun or a star, we can look at the light that's coming in, and we can make some guess about what the temperature of that object is. Could be a bar of iron that we've heated up, and we're looking at its black body radiation, the radiation that's emitted. But if we plotted the frequencies and the, which is actually the different wavelengths that we have, and the intensities, we would actually get some measure. If we knew, we'd actually be able to get some measure of, by looking at the spectrum of what the temperature happens to be. So we can make a series of black body curves, and if we do that, this is in your book, you see something that looks sort of like that, and that's labeled, let's say, at 300 Kelvin. The temperature scale, by the way, Kelvin, is similar to the Celsius scale, but it eliminates the fact that 1 Kelvin is equal to 1 degree Celsius or 1 degree centigrade, but the scale starts at absolute zero. So on this Celsius scale, on the centigrade scale, the zero of temperature is minus 273.15 degrees. That actually equals 0 Kelvin, and this is degrees Celsius. So that would be 0 kelvins, and so 300 kelvins would actually be 26.85 degrees Celsius. So this is a pretty cool object. It's not a very hot object at all. So this would be 300 kelvins. Then we go up to 1,000 Kelvin. That's the next point on the scale. And we get a curve that looks sort of like that. Then we go up to 4,000 Kelvin. And you get something that looks like that. And then finally we go to 10,000 Kelvin. 4,000, I'm sorry, 7,000. So this was 300, 1,000, 4,000, and 7,000 Kelvin. And so at 7,000, it shifts like that. If we superimpose over this, if we look at if we're looking actually down here at the frequency, so we've got the frequency nu here, and this again is intensity. And we can look at our areas of greatest intensity. They keep shifting over here, and what we'll find is that here, this is going to correspond to something that's going to be in the blue region of the spectrum. And over here, this will correspond to something that will be, if we look over here, maybe the red region of the spectrum will be shifted over somewhere around here. I'm not drawing this very well, but we can actually look, and by looking at this, we can see that at say 4,000 Kelvin, well, it's more like maybe about 5,000 Kelvin, that's going to be in the red region, or maybe the yellow or orange region. I'm not sure exactly where, but when we get up to about 7,000, 8,000, 9,000 Kelvin, as a maximum, that's going to be in the blue region of the spectrum. So, I mean, basically what these curves are showing us is we superimpose this little spectral meter over here, and we look at where the the regions of maximum intensity are. We can actually, from that, we can actually, a much better diagram is, I think, is on page 68 of your or 69 of your textbook. It's really 68 and 69 are going to show you this. My drawing really doesn't do this justice, but I just wanted to illustrate this as a way of envisioning the fact that the hotter an object is, the more it's going to be shifted into the blue, and then if it gets hotter and hotter, it's going to shift into the ultraviolet region. If it gets cooler and cooler, it's going to shift into the infrared, and it's going to shift ultimately into regions that we're not even in the visible, anywhere near the visible, whether it's microwave or radio wave regions. And we actually have very cool regions of space where we can actually get electromagnetic information from that happens to be in the radio wave region, and we know that these objects are very, very cold compared to some stars, which can be extraordinarily hot and will shift way into the ultraviolet or even beyond the ultraviolet region. So that's something to consider. Now, there's a couple laws that have to do with luminosity, and we can get there's some interesting things that we can get out of this. We can actually use how the luminosity, how bright an object is, and we can say something about its temperature from that. So there is a couple laws that are introduced in your textbook. One of them. All right, so a couple of the laws that I wanted to discuss with you are something called Wien's law. W-I-E-N''S, Wien's law, named after Wilhelm Wien, a German physicist. And basically what this does, it relates wavelength to temperature. And what it says is, Wien's law, let me erase this. It says that the maximum wavelength, lambda max, is going to be equal to 0.29. If you really wanted to get accurate, it's actually 0.2898, but your book uses, and we'll use 0.29 millimeters divided by T, the temperature, and that's in kelvins. So that actually is a way, if we know what the temperature of the emitting object happens to be, we can calculate what its wavelength would be. But on the other hand, if we've actually measured the wavelength, we can use this to establish what the temperature is. So this is Wien's law. So that's one law that I think you need to familiarize yourself with. Another one is, in your book, is called the Stephan's law. It's actually known as the Stefan-Boltzmann law, to be completely correct. And I think there's, I don't remember what page it's on, but there's a little insert in there that talks about it. Sometimes people use different letters to indicate the same kind of thing. So the Stefan-Boltzmann law generally is the letter that's used frequently is the letter J, and it's actually J star. So J star is what is called the emissive power. Your book uses, I think, the letter F for this, which they call flux. But they both equal the same thing, so it's really the same thing. Sigma, which is the Stefan-Boltzmann constant, constant, and times T, again in Kelvin, to the fourth power. So sigma t to the fourth power. So F is the same thing. It's sigma t to the fourth power, and that's Stefan Boltzmann law. Now, J star, or F if you wish, has the units of joules per second, which is watts per meter squared. So it actually is joules per second times joules per second per meter squared, which is watts. That equals watts per meter squared. So that is a unit of power divided by a unit of area. So it's giving us an indication of how much power is being delivered. Power is energy per unit time. So 1 watt is 1 joule per second being delivered over some particular period of time. And sigma has the units of joules per second per meter squared per unit of temperature, that is per Kelvin to the fourth power. So all these things cancel out, all the other units cancel out once we apply this to the formula, and we're actually left with just an answer that's going to be in watts per meter squared. All these other quantities cancel out. So we can use both of these things to get estimates of the temperature of an object, both Stefan's law and Wien's law as well. Now there's one other thing that we need to consider here, and I think that actually completes this chapter, and that is the Doppler effect. Now, if you've ever experienced, and I'm sure all of you have, an object that is emitting a sound that's moving towards you, and then if it's emitting a sound at a particular frequency, and as the object moves towards you and then it passes you, you'll notice that there is a change in the frequency. So as it's moving towards you, it has a higher pitch, and as it moves away from you, it has a lower pitch. That is to say that the wavelength is actually changing, the apparent wavelength. The wavelength of the sound that is being emitted doesn't change at all, but when it moves towards you, you actually hear one sound, and when it moves away from you, you hear another sound. And this is called a Doppler shift, and this is known as the Doppler effect. So you have it not just for sound waves. I use sound as an example. I use sound as an example because it's something that's a little bit easier to demonstrate. And you can do this very easily. I actually do this sometimes as a demonstration by taking a little, it's actually a guitar tuner that emits a particular note, some note that's on a guitar. It'll emit that frequency, that particular note, and then when I'm in a class of students, I will actually swing this. I have this attached to a rope, and I swing it around and around and around, and as it approaches them, they hear one sound, and as it moves away from them, they hear a different sound. So here's the tuner. And I'm just going to rock it back and forth, and then I'm going to start swinging it in an arc. Okay, so here goes. Well, light does the same thing, as it turns out. So you've got very, very distant galaxies that are moving away from the Earth, and you've also got some other objects that are closer to us that might be moving towards the Earth. And we can actually determine from the change in color, that is the change in wavelength of certain lines that have that if an object is stationary, there are certain lines in its what we call its spectrum, which we'll talk about momentarily. I'll illustrate what a spectrum is. But we can actually look at the light that's being given off from that. And that light, just like the sound Pitch changes. Pitch is a change in frequency. When we're dealing with light, it's a change in color. It's actually a shift to one side or to the other side in terms of frequency. So, for instance, what you'll see is if an object is moving away from you, the lines are going to get bigger. That is we're talking about this. The wavelength will get bigger as the object moves away from you. So it will appear to no longer be like that, but if it's moving fast enough, maybe one of these lines will shift so that it's over here. And now the spacing between here and here is larger than it is between here and here. So nothing has really changed. It's just that this is what we see from the radial. If we're looking radially, if we're looking at this directly at this object and it's moving from our line of sight, it's moving away from us, we would see this shift. And it's called a red shift when it's moving away from us. And if it was moving towards us, we'd see the opposite effect. We would get a blue shift. So, but for very, very distant objects, most of these things seem to be receding from the Earth at a pretty good clip, and we can actually calculate what is known as the recession velocity. But I don't think we'll get into that until the next chapter when we talk about spectral line analysis. We'll get into that a little bit more. So I think, let me just see if I've covered everything that I want to cover here. We talked about the Doppler effect. There is something else in your book on the Doppler effect. It says that here's an equation. It says apparent velocity that is the speed that something seems to be moving divided by its true velocity. I'm sorry, I didn't mean velocity, I meant wavelength. Sorry. The apparent wavelength divided by the true wavelength is equal to the true frequency divided by the apparent frequency. Well, that's just showing this kind of reciprocal relationship between frequency and wavelength. And that's also going to be equal to 1 plus the recession speed, when you say recession velocity. Speed and velocity are not really exactly the same thing. We tend to use them interchangeably, but when we talk about speed, speed is what we call a scalar quantity. It doesn't imply any direction. Velocity is actually a vector quantity. So when I say that I'm moving down a street at 60 miles an hour in my car, moving down the highway, and I haven't specified a direction, that's a scalar. I say my speed is 60 miles an hour. But if I specified in what direction I was moving, then that would be a vector quantity. It has magnitude and it also has direction associated with it. And that is that's a vector quantity. So that's velocity. Velocity is a vector quantity. But we tend to use these things loosely. We tend to use the terms interchangeably. Sometimes I will say velocity when what I really mean is speed. In this case, we probably could call it a velocity because it definitely does have a direction. The direction has to be in the direction of motion, whatever that happens to be. We could specify it, but it's going to be away from our, in this case, we're talking about radial velocity, so it's within our line of sight, and so that kind of does pin it down directionally. It's not just any random direction, and it's not a movement this way or that way. It's a movement either towards us, directly towards us, or directly away from us. So that's a little bit different. Anyway, so this is 1 plus the recession velocity divided by the wave speed. The speed that the wave is moving. If this is electromagnetic radiation, it's moving at the speed of light, essentially. It's moving at a speed of approximately 3.0 times 10 to the 8th meters per second, which is the maximum allowable speed in the universe. You will be pulled over by the photon police if you try to exceed that speed. There is no speed beyond the speed of light, although fairly recently there was some indication that there might have been a certain kind of very small subatomic particle, a neutrino, that appeared to be moving actually faster than the speed of light, but that was found out to be due to experimental error. So the speed of light is still the maximum speed in the universe, the speed of electromagnetic radiation in a vacuum. Electromagnetic radiation, however, does slow down when it's moving through matter of any form. That can slow it down. So light travels much more slowly. For instance, if it's going through water, which is why it appears to bend, which is why when you take a pencil, for instance, and stick it into a cup of water, it seems to go straight down and then it bends once it gets into the water. The image of the pencil seems to bend. That's because light is changing its speed as it passes through the water. Okay, so we talked about the Doppler effect. That really concludes chapter 3.